example, we are going to look at the induced magnetic field and the EMF that's produced when you're changing the magnetic flux in a loop. So we're going to have two wires, and we're making these wires kind of thick. Imagine pieces of metal here. And a third piece of metal is going to pass between these two, right? So all of this conducts. Now this piece is moving from left to right with the velocity of v. Down here, we're going to have a resistor. Doesn't need to be a resistor, but let's put a resistor in over here. And so we have a nice little loop. And let's place this contraption into a uniform magnetic field that is pointing into the page. So we're going to have lots and lots of little X's here that are uniformly spaced, or almost uniformly spaced, if I can draw well. So here's our magnetic field that is populating the space in and around our simple little device. Okay, and as this bar here, as that slides from left to right, we are sweeping up more of these field lines that are pointing into the page. And let's say at any given moment that this has a position of X, and we'll call the separation here, which we'll end up using L. All right, so we're sweeping up more of the magnetic field. And what that's doing, if you remember how we defined flux, right, the flux is the integral of B dotted into dA. Now, we're not changing B. B isn't, the magnetic field itself is not changing. What we're changing here is the area. This area is growing as we pull that bar from left to right. And so what is that going to do? Well, that is going to drive a current, and that current is going to try and fight the addition of more field lines that are pointing into the page. And so in order to fight that, it's going to try and produce a magnetic field. There's going to be an induced magnetic field that has a direction that is out of the page, right? Because if we're sweeping up more field lines that are pointing into the page, we're going to induce a current that drives a magnetic field that points out of the page. And so the direction of the current that is induced is going to have to be counterclockwise. And if we put our fingers on our right hand in the direction of this counterclockwise loop, you're going to see your thumb pointing at you, which is how we get a field that is pointing out of the page. All right, so now let's calculate the induced current. How are we going to do that? Well, we're going to rely on two things. We're going to basically look at Faraday's law, which tells us that the magnitude of the induced EMF is the magnitude of our change in flux over time. And we're also going to use Ohm's law, which in this case is going to be I times R, because we have our resistor up here. And so that's also going to be induced. So we're going to use these two ideas to estimate what ultimately what our induced EMF is, and we're going to get there from our from looking at our current and also looking at our change in magnetic field flux. Okay, so what is our induced EMF? Well, we can just deal with magnitudes here. We already know the direction of the current that it's going to produce from the considerations that we talked about before. where we figured out that the current is going to be counterclockwise. So in order to estimate this, we need to know what the flux is. Well, the flux is going to be B times A, right? And so this is going to be the magnitude of dBA dt. And we can drop the minus sign here and just deal with magnitudes. And so let me just break this out. And so here's our flux. And again, we're just dealing with the magnitude. This is going to be dBA dt. And there's two ways of thinking of this, but B is essentially uniform here, but we can go the long way. So dB dt times A plus dA dt times B. The magnetic field is not changing with time, and so this term is a 0. And dA dt, well, that for sure is changing with time, and our uniform magnetic field is just a constant. And so this ends up being B times dA dt. Well, what is A? A is the product. That's just a geometry here. So that's L times X. And that is within our time derivative. And what's changing with time? Well, L is not changing, but X sure is. And so this becomes BL dx dt. And we know how to describe a change in position over a change in time. Well, that's just the velocity, or the speed in this case, at which our third bar is moving. And so this is our induced EMF. The magnetic field times the separation between those two thick wires or metals times the speed of that third piece. And to estimate the induced current, well, we can get that from Ohm's law. So that's just going to be E over R, or in this case, B times L times V over R. So these are our two important results from this calculation. And the thing to remember is that whenever you're doing this kind of calculation, the direction of your current is going to be set by the opposition to your change in magnetic flux.